Okay, so hello everyone. We will be welcome to session 2 of MathLab Computational Tools. We will be starting in a minute. This session, Aditi will get started with the session. So I think we'll have fun and hope you take as much as you can from this session. We'll try to go slow and we'll try to ensure that if you have any doubts, please feel free to ask in chat here, or if you're attending the live stream on YouTube, please ask your doubts there. We have dedicated chat moderators to clear these doubts. So they will be active all the time and they'll be waiting for your doubts and your responses and your enthusiasm. So please do feel free to ask your doubts.
All right, so yeah, let's get started. Yeah, so good morning, everyone. We're very thrilled to have everyone with us today for session 2 of MathLab. Before we begin, session 1, from session 1, we have a few responses who we would want to give a special shout out for. So these were responses that were sent in until 9:30 a.m. today, and they have like either 100% accuracy or a great amount of effort was put into their work. So yeah, thank you. Yeah, we really appreciate that and thank you for that. So yeah, you have Nikhil, Samudranil, Mosam, Adhavan, Sonalika, Jyoti, Anurag, Nitesh, and Ayush Singh. A special shout out for actually writing Newton-Raphson in C++. Samarth and Chaitanya, Shiva, Ashik, Rutvik, Rohit, Harit, Sumit, Kanishka, Harit, Sumit, okay, Prajwal, Ishu, and Ash. So yeah, a huge shout out to all of you. And we hope you continue with the same for the rest of the 2 sessions as well. Right, this brings us to today's session, numerical methods of computation, which will be taken, the first half of the session will be taken by me, Aditi. I'll be going to my second year and I'm a coordinator of the mathematics club. And the second part will be taken by Pranjal. So yeah, I think we're good to go. All right, so let's start off at a similar note where we left last time. So yeah, and I also wanted to mention that if you have any doubts or if you have any questions or answers to any questions, feel free to write them down in the chat box. There are moderators dedicated towards checking your work over there and helping you out right or wrong. And we encourage that you actually use this tool and be as interactive as you can throughout the session. Yeah, so to begin with, there is a set of images on the left and the right, and they seem to convey the same information, but there's actually a very fundamental difference between these two. If you can think of any, write them down. Again, they will be seen and you will be heard. So the image on the right is of a digital clock, right? It tells you the time, but its degree of accuracy is only limited to the last place of how much time it can tell. It can't be any more accurate than that. For example, if it tells you time in seconds, then you cannot make measurements for milliseconds, etc. And another point is that whatever degree of accuracy you have, it's not very complete. You can always have a time interval that is shorter than that, right? And why this happens is because you're measuring time, which is a continuous process, through a discrete mechanism. So if you really want to tell the exact time, a continuous process, what's a smart workaround around that, right? So the way to go is that you measure a continuous process continuously. And a very trivial example of that is the working of your analog clock. So the continuous process that we choose in this case is the rotation of the hands. So 360 degrees is analogous to some time, and we've been wired to interpret it that way. So yeah, I mean, for the first time when I saw this, even I was kind of perplexed by it, that how can there be such a big difference? So at any snapshot, if the hands of the analog clock are moving continuously enough, the time that you get will be extremely accurate, and there is no discrepancy in the last few digits of the time towards a few seconds, milliseconds, nanoseconds. So that was interesting. And again, building upon that, you have 1/3 and 0.333. There's a key difference here also. So in 0.333, you are never actually at 1/3. You're always free to add a few more recurring decimal places, which give you a better approximation. Whereas 1/3 is exact. You don't really care about how those 3 parts were made, but if and when 3 parts were made accurately, and you chose one of them, then you would have exactly 1/3. So it's more of an idea than something that it's more of an concept of fractions, which we don't think about so much in our daily life. And we tend to think that the decimal representations and fractions are the same, but actually they're not. So if you notice that on the right, both of them, for both the cases, you can add a few more decimal places, get an exact answer. And this is exactly how our systems work, systems that we've created to measure, right? They always have something we call a least count. Computers also have, there's only a certain degree of accuracy that you can get through a computer. So we operate under the realm of 2 constraints. The first being, you cannot get values as small as you like. They come at a cost. And the second thing, you can't even store, and even storing data is expensive, right? So this is exactly where numerical computation comes in, because this is the crux behind how computation is actually carried out in computers, right? So, and we are engineers, and we want to model real life situations. We don't want hypothetical answers. So we try to end the answer as close to the actual analytical answer. And this is your actual analytical answer. And this is exactly where we left off last time, right? Moving on. Okay, so this is something I expect a lot of people to actually have a good idea about. So we'll just go through these questions here. Say I know the value of a function at a point, as well as its derivative at that point. Is there something that can be said about points lying close by? If you know, please answer in the chat. Yeah, so let's take a look at this animation for the sake of clarity. At roughly this point, which looks like 26 on the x-axis, a tangent has been sketched. And so you know the value of the function at that point. You also know the derivative. The green line represents the tangent line. And you can see that for a pretty reasonable area, the tangent line and the curve actually overlay each other, right? So what can be said? The better way to say is that the tangent line approximates the curve at that point. The second question, do you notice any problems with this method? So I'm just going to play this animation. Right. So the purple circle, it represents the scope of the region of interest. And as you can see, as I increase that, the tangent line begins to massively falter. So it's only good up to a few places, right? So that's the problem. It works for points close by. The tangent line is a pretty good approximation. And another question I have here is, can you think of a function where this approximation is 100% accurate? So yeah, I'm going to leave that to you and the moderators to do it in the chat. Yeah, so this is exactly what a linear approximation is, in case anyone didn't know. Right. Okay, so let's make a few changes to the first problem. you have information about the value of a derivative at a point on the function. So you have the first order differential equation over here. What really is a first order differential equation? If you have dy by dx, it's essentially giving you the slope of the tangent at every point on the line. So you have value of the derivative over here, and you're also provided with one set of values that satisfy the equation. This represents a family of curves, and this pinpoints to the exact function that you want to check. So what are we trying to achieve here? You want to rebuild the function that satisfies this derivative and the given set of points. The only catch here is that you cannot integrate. So,
hey Aditi,
yeah.
could you just represent this part again? I think your video is slightly frozen.
Okay. Have I been audible the whole time?
Yes, you have been audible.
All right. Wait. So you want me to stop sharing and start again?
Maybe try turning off your video and present. Maybe it might maybe the presentation might be a little smoother.
Is this better? Atreya?
Your video isn't visible for me.
Okay, because it's
can others see it?
turned on for me.
Okay, try to reshare once.
Okay, give me a minute. The screen is visible?
Content is not visible right now.
Can you see
Okay,
the presentation? Yeah, fine. I'll rejoin the meeting. Maybe that should work.
Yeah, try to rejoin the meeting.
I'm sorry about this.
Your screen is visible right now.
Okay, cool. And video also now.
Yes.
Okay, nice. See numeric computers and their shortcomings. Analytical computer is probably what have happened. Yeah. Okay, so was this explained? That the slide explained?
We couldn't see the slide. I think the video paused at the last slide.
Oh, okay, fine. Yeah, okay, so I think everyone was with me till here, and after that I lost connection. Yeah, so yeah, let's make a few changes to the first problem. You have a differential equation over here. It's a first order derivative, which gives you a family of curves. And from that family of curves, by specifying the point, we decide what curve we want to, or function we want to work on. So your task is to rebuild the function, but the catch over here is you cannot integrate. So if you can think of any ways, that would be interesting. But yeah, let's move on. So how do we go about this, right? The idea is pretty simple. The intuition behind this is pretty simple. If you sample a nice number of points on this, and you know the order in which they are supposed to be done, in 1 after 2, 2 after 3, so on and so forth. And even if you're very bad at drawing, you will still be able to come up with this figure quite neatly. So that's the idea. And how do you go about this? The idea comes from a linear approximation. So between every 2 points, you make some kind of a linear interpolation. So let's actually see how this builds before getting into the actual method. And I'd encourage that you try to think of this on your own. We'll discuss the whole algorithm later, but up to then. Right. So this is your actual function, the blue line. And what we have created is we have built the function on the red line. The red line is a function that we have built. And the points that we are sampling is after every 5. So if you see 0 to 5, then 5 to 10, 10 to 15, 15 to 20, and 20 to 25. So it's exactly there where our, you can see the slope of this is changing. So since the slope is changing, what you can say is that we know the derivative of those places is changing. So we're taking input about around 5 points in the given domain, and then we're trying to build upon this function. Yeah, so the step size over here is equals to 5. This is incorrect. Yeah, I think it. And we'll now the step size here should be 1. We'll see what happens if instead of sampling at every 5 points, if you haven't understood what's exactly happening, that's fine too. I just want to give some kind of a notion as to how this plays out actually. Instead of sampling every 5 points, we're sampling every 1 point over here. So let's see what kind of changes that makes. So as you can see, the function that we are, the red line is the function that we are sketching. It's much better and it's much closer to the actual function compared to what we did last time. We can actually look at it for a particular point. Yeah, so see, at x is equals to 10, the value of the actual function is 160, but the value that we got was 85, which is pretty bad. And we'll do the same thing over here. Stop this at x is equals to 10. Yeah, it's 145. So from just by sampling points closer together, we've gone from 85 to 145, which is a far better approximation. So you can see that you're actually building the function over every small step that you're taking instead of integrating it. So now coming to the algorithm as to how this actually works. So you can be pretty sure of the first point on the graph since it's already provided, that was 0, 0. And you know the derivative at that point. And not only at that point, you know the derivative at every point thanks to your differential equation. And you also know that for a reasonable distance on the tangent line, the tangent line approximates the curve. So what I can do is I know the point, I know the derivative, just sketch the tangent line at that point for your small distance or step size. So the next point you pick should lie close to the previous point and somewhere on the tangent line. And this is exactly what Euler's method of numerical integration is. It's pretty intuitive if you come to think of it. That's why we recommended trying to get a grasp of this on your own. All right, so a small quiz. Which of the following will make your results more precise? Reducing step size, including higher order derivatives, assuming, okay, a non-linear interpolation. Let me just explain that. Yeah, so here, yeah, here when you connected points 2 and 3, you assume that the line will be straight. A non-linear interpolation is basically letting go of that assumption. And we will take around, we'll have around 2-3 minutes for you guys to submit your responses to that question. It's a multiple option correct question. And I think even if you don't get all options right, at this point of time, it's okay, because we'll cover some stuff later on through the session. So yeah, we'll wait for a few minutes for you guys to answer. I hope the poll is ready. Yeah, this is a multiple option correct question. But yeah, it's fine. One, you can put in any options that you find accurate. Yeah, I'll show a slide here. Sorry. Yes, these are your 4 options. Yeah, and okay, UN 16 is just using 16 bytes of your memory. Like it's more storage. It allows you to store more information compared to UN 8. And you're using a computer to do this. Let me make that assumption clear. We will discuss solutions in a bit, or just put answers right now. We'll wait for like just 1 more minute, probably. We'll start. Yeah, I think we'll continue. Yeah, we'll get back to the solution of this question. We'll discuss some more and we'll get back. Yeah, so I'll resume. Okay, so interesting answers. We'll see what the correct ones are. Before that, let's go over something called error analysis. Now, we've spoken so much about numerical methods and how they're different. It's important to see how error is being generated by our very own computers, which kicked me out a few minutes ago. So firstly, precision errors, right? Exactly. Numbers as recurring decimal places. How would you store them in a computer? You don't have infinite amount of memory to allocate to just one number because the decimal places are recurring. And every time you cut off something, you're actually losing information. And say you're running an experiment, whatever the least count of your apparatus is, if you have more decimal places than that, then that's not even useful, right? So these sometimes precision errors show up quite badly when what you want to compute actually requires that degree of precision. Then this becomes a problem. And the second thing is discretization errors. So I'm pretty sure a lot of you are familiar with this. This is Taylor series, and this is like the holy grail of finding the value of a function at another point. X minus, so how this works. F of x, this is the point that you want to find. F of a is the information of the point that you already have. X minus a is the distance between the point you want to find and the point you have, which is equivalent to a step size in this situation. I hope that's clear for someone who didn't know what Taylor's series was. So if you look at this closely, up to now, we've taken f of x, f of a, and we've considered the first derivative. Terms after this have completely been chucked off. So that shows up as error because Taylor series is 100% accurate. We cannot get into the proof of Taylor series right now, but if you go to think of it, it does make sense that you add more. You may not know the actual value of a function at the point, but if you have information about all required derivatives, you are good to go. But with Euler's method, we've restricted ourselves to only the first derivative. So all these other terms from f double dash a to the as many terms as are non-zero, they show up as errors. Now there are two kinds of errors. One is local error, so error that shows up at each step. So what local error basically assumes that the step that you took before it was accurate. How much error has built upon that? So I'm assuming f of x is absolutely correct. F of a is absolutely correct. I'm finding f of x, hiding all these other terms. So this is your error. And since x minus a is your step size, which we will call h from now on, your local error is proportional to h square. A lot of you might ask, but there are terms of h to the power n which are greater than square. The thing is that we're assuming h to be less than 1. So h square is greater than h to the power n. And that's the highest degree of error. So we'll call the error proportional to h square. And then you have global errors. So the thing with local errors is that you assumed that this was correct. However, this was also not correct because this was also derived from a point before that. So the net accumulated errors, that is local error into the total number of steps you took. So h square into something is your global error. And it would be nice if you could actually tell the proportionality in the chart. For local error, for global error, sorry. Local is proportional to h square. All right, so I'll give the answer. H square into number of steps. So say L is the domain or the part that you're interested. You have to find number of steps. So you divide it by the width of each step, that is L by H. So H square into L by H, global error is proportional to H. And yes, H is worse than H square because H is less than 1 here. I hope the error analysis part is clear. All right, so coming to the correct answers for our questions. The first option, reducing step size, yeah, that actually works. We saw how changing the step size from 5 to 1 give a better approximation. So yes, that definitely works. That's correct. Including a few higher order derivatives. Now, since we saw what Taylor series is, the more derivatives you include in your function, the better approximations you get. So even that works because that gives you a more accurate response for f of x. Assuming a non-linear interpolation. So what makes this, what makes our thing linear? What makes Euler's method linear is that we only consider to this term. Starting from this term onwards, it cannot be linear anymore because if you're including the second derivative, you have to include the square term also. And yeah, option D, using u and 16 instead of u and 8. This also gives more precise answers because of the precision errors that we saw. If you increase storage space, then obviously your answers will tend to be more accurate. I hope the options are clear. We'll stop for a few minutes for attendance. Yeah, chat mods, you guys can give attendance. You can post attendance now. Yeah, okay, yeah, we'll go over option C and D again. Yeah, just a minute. Where did that go? Okay, so did you understand till option B? Yeah, okay. So option B was clear. So the thing is that yeah. So what is a linear interpolation? So when you're joining points, you're using a straight line. If you stop using a straight line, your interpolation is basically for you're considering every fifth point or every next natural number while finding the derivative. So for points between that, you do something, you interpolate. Basically, you just join them. If you join them in a straight line, it is linear, and if you don't use a straight line, then it's non-linear. So if you have included so I hope this is clear that you have included f dash a in Euler's method. But if you want a more accurate response for f of x, you use f double dash a. Now, when you write it, like you included x minus a term here, you would have to include x minus a square term also. And as soon as x minus a square happens, it becomes nonlinear. I hope that's clear. And yeah, option D is increasing storage space. So we saw that errors show up due to precision because computers enable us to only store a finite amount of finite amount of memory, right? So if there are a lot of decimal places, and if you have the capacity to include more, your answer will be more precise, and that's exactly what the question was. Is it clear now? Okay, interesting, when you know the nature of the curve, if the curve is linear, obviously you don't need a non-linear interpolation. But the nice thing about that is your double derivative also goes to 0. D square y by dx square. That will also go to 0, since dy by dx is only a function of x and not of x square. So automatically that term vanishes. I hope that's clear. Okay, yeah, global error is proportional to h. Okay, global error proportional to the global error is local error into the number of steps, because at every step thus far, error has been built. Okay, so we'll continue. Yeah, we'll move on to the next thing. If you have questions, I think in the chat they will be answered. Yeah. So we saw Euler's method, and we saw that it's not even very accurate. We've come up with a few modifications to Euler's method that. Okay, I'm getting a response to wait for just a couple of minutes more. I will do that. Is my presentation visible?
Yes, your presentation is visible.
Yeah, okay.
Yes, Someshwar, you're raising your hand. Do you have any question? You can unmute and ask a question if you want.
Yeah. So modifications and new methods. So yeah, there are some very fundamental problems with Euler's method. The main being that you're assuming the value of the derivative to be the same throughout each interval or time step. But obviously that is not the case, right? So how do you fix that? And the thing that we've come up with to make these corrections is you first make a prediction using Euler, and then you make some correction to it. And hence they're also called predictor corrector methods. And if you want to check how much error you're generating through your own new method, whatever that is, you simply substitute in Taylor series and see how it works. Okay, so we'll take a look at the first method. So the first method is midpoint method. Now, one differential notice here is that your derivative is a function of both variables here from here on. So it's a little slight hint at multivariable calculus, but nothing very hard, right? So your predictor step is basically your Euler step. So what you're doing is, in your predictor step, instead of taking the full step of h, you take it at only h by 2. And you know that reducing step size reduces error. So this will definitely be more accurate. And in your corrector step, that is the step that you will take to minimize the error. So first you find this, what this is at exactly half the step size. And then what you actually plot is your corrector step, not your predictor step, if I confused anyone. So here, this is what you will be substituting for your derivative will no longer be the derivative at the initial point. It will be the derivative at the midpoint, which does seem a lot more sensible, given that you're using the same derivative throughout the entire interval. It makes a lot more sense to use the derivative at the midpoint than to use the derivative at the initial point. And this actually has significance when we analyze the error over here. So the error, local error, also known as local truncation error. So how do you obtain that? That is, first you apply a Taylor series expansion on the previous term. Again, the previous term for both of these is the same. This is capital Yn plus 1. This is small yn plus 1. So they're representing two different things. They're representing one step after a previous term, and in both the cases, the previous terms are the same. So this one, the difference, where's the difference then, right? If the previous terms are the same. The difference is in terms of how the next term is obtained. So capital Yn plus 1 is applied by doing a Taylor's expansion of the previous term, and the small yn plus 1 is obtained via midpoint method. That is the method that we've discussed here. So just a brief synopsis of this. You start at a point, you do an Euler's approximation for a point at half the step size. You find, and when you're actually applying the algorithm, instead of using the derivative at the initial point, you use the derivative at this new point, which is midway. I hope this is clear. Then we'll go to the next part. Okay, so yeah, so for those of you who've seen multivariable calculus, this won't be that painful, but for the rest of us, we'll see. So just look at this for right now, right? We said we are applying a Taylor's expansion of the previous term, and that's exactly what we're doing. So The previous term in both cases is the same. Small yn, capital Yn, both are same. We've taken only small yn here. And we've applied a Taylor series expansion. So that x minus a is h. Your first derivative, h squared by 2, that is x minus a squared by 2 factorial. That term is also very understandable. The problem will come when you will try to compute the second f double dash of a, because now you have two variables. But I think we did see in the last session how these kinds of derivatives work. So you take a part, so the important thing to remember is f t of y is already a derivative with respect to t. D by dt of that is like taking its derivative once again. So even if you don't understand how this works, it's not that important. So you basically take derivatives with respect to the individual variables. So dou f by dou y. Again, f is already a derivative. Let me remind you, that's what's showing up here. F dash of x into x minus a. F dash of a into x minus a. X minus a is h. And f dash of a is this term, which is already a derivative. So, a lot of people get confused because they think that a derivative term should come here. But yeah, we've already mentioned that f t comma y is dy by dt. So this is how you compute your second derivative. Simply substitute it over here. And the next term that you get will be something h cubed by 3 factorial. So it's something of the order cube. So that is the first term for you. That is this side, yn plus 1. Let's go to the thing that we obtain via midpoint method now. Okay, so first things first, multivariable Taylor series. What we saw Taylor series was for f, x plus a. But what if there are two variables, and how does that work? So first, obviously, f of x comma y. Then h is the increment from h. K is the increment from your other variable. So h into the partial derivative with respect to x plus k into the partial with respect to y. And after this, all your terms will be of the second derivative. So terms like h square, k square, 2hk, so on will start showing up. But for us, since we are applying Euler's, and Euler's concerns itself with only the first derivative, we don't need Taylor's expansion beyond this point, except for knowing the fact that after this, the proportionality is with h square, which is the increment from h, and there'll be a term having k square, and one term logically, if there's h square, k square, and the combination of both is also possible. That's where 2kh comes from. And when you write for the cubic term, you will find all your 3c, all your permutations and combinations of the third term possible over there. But we'll skip that for now. So applying exactly, this h square and k square. So when you write when you write Taylor's expansion for this, you will get terms. You will get in terms of h square and k square. I'm sorry if this is confusing anyone to think that h square into k square. It's not like that. There'll be one term having h square. There'll be another term having k square. But the important thing is that the order of this will be h square, since we are assuming that the increment in step is less than 1. I hope that's clear now, what it means. Okay, fine. We'll continue. And then you make that substitution over here. So in place of h, x plus h, you have t plus h by 2. In place of y plus k, you have y plus what was obtained over here. I will probably not go very deep into this, but yeah, it's pretty understandable. You're doing a Taylor series approximation for this. So h by 2 over here is nothing but h over here, and f of x here is f of t here. So that's where this term comes from. f of y here is the same thing over here, and your increment, that is h by 2, fy of t comes over here. I think that's pretty clear. So when you write yn plus 1 in terms of yn plus in terms of your yn plus your h into the derivative, this is what you get. All h square terms go away, leaving your local truncation error proportional to h cube. As we saw in Euler's, it was proportional to h square. And again, h cube is better than h square because we are assuming that h is less than 1. If this is not very clear, it's fine because it requires a little bit of understanding of. Yeah, okay. So let's leave the proof. The proof is something that anyone can do if you know how it has to be done. We'll go over this thing once again. So a predictor step, you know Euler's isn't accurate. So you make a prediction and you try to correct it in some manner. So in your predictor step, instead of going the whole distance h, you're taking a step and that step size is h. Instead of taking the whole step size, you take half the step size over here. And in your corrector step over here, you use the derivative at that point because the differential equation will be, you use the derivative. See, the differential equation is a function of t and y. It's not only a function of x like it was last time. So yi, that is your previous value, and h into some derivative. The derivative that you are using this time is the derivative found at the midpoint versus the derivative found at the initial point in Euler's method. If the intuition is clear, we'll move on. I mean, the error and all is fine. That's self. You can do it on your own anytime later. Okay, so you'll probably need to think about it a little bit, but it's not that hard. So there's another method called Yoon's method, where what we did last time is we went to the midpoint, found the slope, and used that. But what we do for this method is instead of taking the slope at the midpoint, you find the slope at your initial point, the predictor point, and take an average of those two and use it. Does this make sense? So here too, all your h square terms go away, leaving your error proportional to h cubed. Okay, so yeah, the next part, are straight lines the way to go? Most of you already answered this in that question. That other approximations are pretty possible and reasonable too. So we'll look at, I want you to look at this animation. So far we've tried to retrieve a function from its differential, from its differential equation, its first order derivative. We are trying to find an alternate for integration only. It's equivalent to integrating it, but not by the conventional method, by using approximations. That's what we have done so far. So here, so what's happening here is we're taking 3 points and we're finding the parabola which approximates it in the best way. Okay, previous slide. Yes. Is there anything, wait, I'll switch to Teams. Is there anything that needs to be explained again here? Is this clear? Okay, you want an explanation for this. Okay. So for what we did, okay, first Euler's method, the very basic thing. You start at a point, find the derivative at that point, use that derivative for the whole step h. Then midpoint method. You start at a point, but you're going to travel a whole step size of h. So instead of using the derivative at the initial point, you use the derivative at the midpoint for the whole step size. And then very similar to this is this method. And what you do here is find the derivative at the initial point, find the derivative even at the next point, which you would have found for Euler's method. But you use an average of those two over here. See, again, the only problem with Euler's method is you're assuming that the derivative remains constant throughout your step size. I hope that's clear now. All right, nice. Moving on, yeah. So yeah, this animation suggests that yeah, if you have 3 points, you can easily find a parabola which approximates those points. And yeah, the function here is x cubed plus x squared plus 6. Yeah, it probably looks like it's 0, but the first interval is 2000, so 6 looks like it lies on 0, but no, that's not the case. So there is a rule that helps us do these integrations. So solving, you understand it, solving a differential equation is equivalent to just doing the integration, which is equivalent to finding the area of a curve given a function. Finding the function given a differential equation, the tool that you use is the same when you want to find the area under the curve, given that you have the function with you. So like you saw over here, there's a parabola which is approximating every 3 points. So now instead of finding the area under the function, we'll find the area under the parabola with this and this limit. And then there's something called Simpson's 1/3 rule, which helps us do this very easily. So what you do is that for whatever area you have to integrate, what Simpson says is that it's equivalent to whatever h is, again your step size. So h by 3. Your first and last points, you write the value of the function as it is over those 2 points. And then you alternate with 4 and 2 weights for even and odd places respectively. The proof of this is quite tedious. We will not go through that right now. But if you want to take a look, we use this rule in approximating the area under the parabola. Because if you actually have to do ax squared plus bx plus c, that and then integrated, find a, find b, find c, that is your the leading coefficients of your parabola, that's quite tedious. So better than that, you use this rule. So fa and fb are your 2 boundary points. You write them as it is, and then you weight this by 4 over here. So you use Simpson's rule, and if instead of using 3 points, if I use 5 points for approximating the area under the parabola, I would go 1, 2, 3, 4, and 5. I would use 5 points. FA and FB, that is your starting and initial points, should have been the same, and then you have 3 more points that you have chosen that you have to add. So the first one would be multiplied by 4, then by 2, and then by 4 again. But since you have only 3 points, you write the boundary points first, FA and FB, and then you start weighting them even and odd, like 4 and 2 respectively. Odd and even, 4 and 2 respectively. So that is Simpson's 1/3 rule. The interesting thing about this is just doing this much makes your error proportional to h to the power 5, which is again a far, far better situation than Euler's or your modified Euler's method. And if you want to read a little bit more, I've attached this link over here. It's a nice explanation I found on the internet for this. If you're very into and really want the proof, and if you want the proof for this, just this much, I have that too. It will be shared later. Yes, that's it from me. Thank you. Yeah, higher the power of h, lower the error is, assuming that h is less than 1. Yeah, we'll share the second attendance link now. And Pranjal will continue after this. Thanks a lot, everybody. Yeah, doubts. Yeah, we can take a few questions. Attendance and doubts now. Yeah, 3 by 8 Simpsons is also another method. The only difference in 3 by 8 Simpsons is that here the weight for this is 2, 4, 2, 4, so on. For 3 8 Simpsons, the way that you weight your functions is slightly different. Nice question. Wait, I'll share my screen. Okay, so is this curve a parabola? No, right? It's working for any general curve. What we chose here was a parabola. We want to find its area easily, and we are using Simpson's rule for that. Simpson's rule doesn't really have much to do with parabolas. We're using Simpson's rule to make our life a little bit easier. I hope that answers your question. Okay, yeah, Yuan's method is improved Euler's method. It's exactly that. Predicting by Euler's method and making some correction to it. Yes. Yeah, I think Dina answered the question.
Yeah, am I audible and visible?
Yes, you are.
Okay, let me share my screen. My screen is visible, right? Okay, so hey guys, I'm Pranjal Vashne. I'm one of the coordinators of the mathematics club here at IIT Madras. And now you'll be learning the basics of GNU Octave and whatever you have learned in the last part, like the Euler's method. I'll code for that, and I'll give a basic intro to method or differences, and I'll also code for it. Okay, and I hope everyone has installed Octave and it's able to run code. And if you guys haven't, then it's totally fine. You guys can just learn how to write code and then you can implement it yourselves later on after the session. We'll anyway be sharing the slides. Okay, so let's begin. So what is Octave? Like, why do we use Octave? So Octave is used for scientific computing and numerical computation. It is used to solve linear and non-linear problems. So like you have learned the Euler's method, right? I'll be teaching you how to numerically compute Euler's method and another method called the method of differences. And if you guys have learned about signal processing, the Octave is very helpful for signal processing as well. And Octave has got inbuilt tools to like plot data and analyze data. So that's why we'll be using Octave. It's very efficient in some tasks. Know that Octave is case sensitive. So by case sensitive, what I mean is suppose there's a command CLC. So that command will be only be executed if it's written in small letter, that is small CLC. And if you type in any capital letter or in some other format only, then it will throw an error. It won't run. So yeah, please know that while you're writing your code. Okay. Let's go to the basic commands and operations in Octave. So there are two basic commands, clear all and CLC. And I'll be discussing what they do later on in when I code, not now. And there are two other commands, disp and input. So disp command is used when you want the user to read some message, and input command is used when you want the user's input to take in into some variable that you have defined. Okay, and there are a few basic operations that you can do on Octave. You can do arithmetic operations very efficiently, like it's very easy and fast to do on Octave. And you can define arrays. And if you guys don't know what an array is, it's basically a matrix. Okay, and you can create loops and functions. This makes your code run faster and the debugging time becomes shorter. Like even the length of the code becomes shorter if you use loops and functions. And as I've said before, yeah, you can plot data very efficiently and you can analyze it. Okay, so let's begin with the basics of Octave. So to display something, you use the disp command, and this is the syntax for disp. So you write in disp, and whatever message you want the user to read, you will write that in brackets and under double quotes. So if you want the person to read "Hello World," this is how you will write the code for it. Okay, and if you have defined a variable x, and you want the user's input to be stored in x, this is the syntax for that. X is equals to input and whatever message you want the user to read. So that will again come in brackets and semicolon. And after the user reads the message, he will type in whatever is required. Like here it's enter number. So the user will type in the number. Okay. So yeah, remember that if you keep a semicolon at the end of any line of code, it makes that line run in the background. So like I'll show you with an example when we code. Okay, yeah. So let's begin our first Octave program. Let's switch to Octave. Hope you guys are ready with that. Okay, so before we begin, you guys have to first get a folder. Okay, this folder will contain all your code files. So it's preferred that you save a folder in the C drive, and then to load that folder here, you can load it in the file browser on the top left. You guys can see that, right? So for that, you can just type in the file path. Like I've already created my folder, math demo, and I've already loaded it here as well. So, and then after that, after you load it, you have to click enter. Okay, and you see 4 tabs on the bottom, right? Command window, documentation, variable editor, and editor. You'll be using only the command window and editor for now. The editor is where you'll be writing in the code, and the command window, like this is the editor which I'm showing you right now. And the command window is where you will run the code. This is where the output of the code will show up. Okay. And to create a new file or to create a new script, on the top left, you see a green plus on a blank page, right? The new script. So you click on that and a new script gets generated. Okay. So let's begin with the first program. So first we'll see how to display a message. So you type in disp and brackets and double quotes. Let's say I love math. Okay. And we'll hit a semicolon. See, we can put a semicolon after disp and input commands because the command is forced to run. It doesn't matter like I've told you that if you keep a semicolon after every line, it runs in the background, right? But in case of disp and input, the Octave forces the command to run and it will show up to the user. Okay, so first we'll save this file. And let me call my file basics. Save. And it will show up on the top left in the file browser. And we'll run this. Right click and run. Okay, so let's go to command window. And oh, wait, I haven't loaded my folder properly. 1 second. Give me a second. Let's name a new folder, demo, and then we'll load this folder on Octave. Okay. So let's close Octave. And to load the folder, you can go to C drive / and then demo and then enter. And let's type in a program again. So this I love math. We'll save it as basic. It should be saved in demo folder and we'll save it. And now let's run this. So as you can see in the command window, the output comes out I love math. That was expected. Okay. And now let's do some basic arithmetic operations. Like suppose you just want to display what 2 plus 2 is. So you can just type in 2 plus 2. Unlike other programming languages, you can just type it like that and you can save it and run it. As you can see, it says I love math, which was our previous code line, and answer is equals to 4. Now let's define variables and let's do some operations on that. Okay, so let x be 2, and I'll put a semicolon at the end because I do not want the user to see that x is 2. Okay, and let y is equals to 3, semicolon. I'll define a new variable called sum, or let's give it z. This z will basically be the output of x plus y. So z is equals to x plus y, semicolon. And I want the user to see what z is, right? So I'll simply put z. Okay. And I'll save this and I'll run it. So as you can see, it says I love math and z is equals to 5. Now observe that all the outputs of the previous codes are displayed as well, right? To clear this, you can use the command CLC, which I've told you earlier. It's a good habit to always put this command CLC. There's one more command called clear all. On the left side, you see the workspace, right, which contains all the variables and the data types. It will clear when the clear all command gets run, it clears all the stored variables of the previous run. Okay, so it's always a good habit to write clear all and CLC on the top of your code. So clear all and CLC. Okay, and if you want, we can run this program again. Yeah, as you can see, it's like the previous outputs have been cleared and a new output has been generated. Okay, so now let's see how we can take in the user's inputs for our variables. Okay, so x is equals to input, and then always note that between the disk command and the next bracket, like this bracket, there should be no space, and the same goes for input. So the bracket after input, there should not be any space between input and bracket. Okay, so input, enter your first number. We'll just add up the two numbers, the thing which I've done before. So enter your first number. Okay. And then we'll hit a semicolon. Pi is equals to input. Enter your second number. Okay. And then z is equals to x plus y. And we'll print z. So save it and run. So enter my first number. Let's enter 10. Then let's enter 23. The answer is 33 and it displays that. Okay, so I hope you guys are clear with the basics. I'll take a 2-minute break and you guys can experiment with these. I'll take your doubts. You guys can ask your doubts and I'll address them. Okay. So was it clear? Was everything clear till now? Could you guys properly code? Okay, cool. Please show how to create a file. Yeah, sure. So you on the top left, you see a green plus on a black page, right? It says new script. So you just have to click on that and you can write your code and then you hit Control S. Control S is basically save. And then you can give your file name and run the run the file. That's it. Please repeat CLC and clear all command. Please explain this semicolon again. Okay, I'll explain what CLC and clear all is. So see, suppose I remove clear all and CLC, okay? And I just simply run this. In my command window, the previous run's output is displayed, right? On the top, you can see I love math, enter your first number 10, enter second number 23, and then it goes to 33. This was the output of the previous run. Right now, I don't want this to come again. I want a fresh, I want it to be a fresh like output, right? So for that, you use CLC. CLC will clear the previous run's output and clear all. And if I type in clear all, it basically clears the values which are stored in the variables in the previous run. Like previously, I stored x is equals to 10, right? So now it will remove x. It will remove the value of 10 from x. It will take in my new variable, like my new value of the variable. So that's why you use clear all. And a semicolon. Okay, let me explain you what a semicolon is. So suppose I given x is equals to 2 without a semicolon. Okay, and I give y is equals to 3, and I hit a semicolon, and then z is equals to x plus y. Okay, and then I print z. Okay, so let's save this and run it. So what is the meaning of this? Like what are we expecting from the output? The output should be x equals to 2 and the value of z, which should be 5. And y should not come. Y equals to 3 should not come because I've kept a semicolon at the end of the line. So that makes the command run in the background. So let's run this and see what the output is. As you can see, okay. Seems to be an issue with the file. One sec. Yeah. So now suppose let me remove the semicolon at the end of the line x equals to 2 and let's run the code. Okay. So let's run it. As you can see, it displays x equals to 2 as well as the output z is equals to 5. And it doesn't display y is equals to 3 because I put a semicolon at the end. So I hope that's clear. I'm not sure why are there a few lines between z and 7. Something there could probably be an issue with your formatting. That's weird. Okay, I'll just continue for now. You guys can ask it out later. So give me a second. Okay, so let's go back to a presentation. So the basic stuff is done. Let's proceed. Let's go on to arrays. So what is an array? An array is basically used to store a collection of elements, and each of the element is identified by an index. Like suppose you want to store, the first and natural numbers. Okay. Now you wouldn't want to create many variables for that. You can create an array, and each element of the array will contain a natural number from 1 to 10. Okay. So there are 3 types of arrays: 1D array, 2D array, and a 3D array. A 1D array is basically an array, like it's basically a row, and the row will contain your elements. And a 1D array is basically a one-dimensional array, and a 2D array is a two-dimensional array. It's basically a matrix. If you guys know what a matrix is, I mean, you guys would obviously be knowing. And it will basically have rows and columns. And suppose you want a 3 into 5 matrix, so it will have. So my 2D array will have 15 elements. Okay. So let's go to Octave and see how do we define an array and initialize it. Yes, so let's define a variable A, which is my array. And inside my box, like I'll keep a box bracket, and inside my box, I'll keep the elements of my array. Okay, so suppose I want my the elements to be 1 to 10. So that take a lot of time. So let's see for 1 to 5. 1, 2, 3, 4, 5. And then we'll print our array. Okay. Let's see what the output is. As you can see, it prints the elements of the array. So, but now what if I wanted to print elements from 1 to 20? It will take a lot of time to manually like write it down, right? So there's a shortcut to it. It's basically the first element colon the last element. Okay. So 1 colon 20, because I want to print elements from 1 to 20. I mean, I want the elements from 1 to 20 to be stored in my array. So let's run. Let's see what the output is. Okay, yeah. So the output like 1 to 20 cannot fit in just one line, right? So like if I reduce the size, it can probably fit in one line. But because of space issue, it has shown the output in two lines. So like columns from 1 to 13 and columns from 14 to 20. Okay. Yeah. So now what if I wanted to print elements? What if I wanted my elements to be from 1 to 20, and between two numbers there's a difference of 3? By that, what I mean is I wanted my elements to be 1, 4, 7, 10, 13, and so on. Okay. So again, there's a shortcut to it. It's just an addition to this. It's going to be the first number, colon, the step difference, which is 3, like the difference, which is 3, and then colon the last number. So 1 colon 3 colon 20. Okay. We'll save it and run. As you can see, it displays the numbers 1, 4, 7, 10, 13, 16, 19, which is what we wanted. And it won't display 20 because 20 is not 1 mod 3, like it won't be generated in the sequence. Okay, so that's it for a 1D array. Let's move forward to a 2D array. Okay, so a 2D array, for getting a 2D array, it's the same as getting a 1D array, except after you type in the elements of every row, you'll put a semicolon. A semicolon would mean go to the next row and consider the elements from there. Okay, so suppose I wanted to create a 2 into 3 matrix, and my first row has 1, 2, 3, the elements, and my second row has 4, 5, 6. Okay, so 1, 2, 3, a semicolon, and then 4, 5, 6. Okay, and then let's display my array. As you can see, my array is shown. Now I'll teach you a concept called indexing. So as you can see, like the first element is 1. So the index of that is 1, 1. What is an index? An index is basically an identifier to an element of the array. So and the index for 2, like which is the second element, is 1, 2. Is basically row, column. Okay, the index is row, column. So if I wanted to print what the value is in the 2, 3 element of the array. So for that, I can simply do A and then brackets 2, 3. Okay. And always remember that indexes start from 1, not from 0. Unlike other programming languages like Python and C, the index start from 0, but here the index start from 1. Okay. So the 2, 3 elements should be 6, right? So let's see what Octave gives us. Yeah, it gives us 6. So that is called indexing. I hope you guys understood this part. So let's proceed forward. So this is a 2D array, and this is indexing, which I've just taught. Okay, now loops. So what's a loop? Like, what's a loop used for? It's basically to execute a group of instructions multiple times until a certain condition is met. Like if I want to display my a number from 1 to 5, I want to display numbers from 1 to 5. Instead of writing them manually, I can create a loop and display them until a condition. My condition here will be till I is less than equals to 5, it will display I. Okay. So there are two types, and it will be why we're using loops is so that it can save our time. It can shorten the length of our code, right? So that's why we use loops. Okay, and there are two types of loops: a for loop and a while loop. So there's no difference between these as such. Like there's obviously a difference in syntax, but you can use both of them. And in some programs, you will find it easier to use a for loop, and in some others, you will find it more better to use a while loop. Okay, so let's see how do we create for loop. So a for loop. So in this example, I've displayed numbers from k is equal to 0 to 5. So I have taken my variable k and I'm going to start with 0, and I want it to like increment after every loop and display what k is, right? So I want my condition is that it will display k till k is less than equals to 5. So let's see how do we do that on Octave. So my for loop will be like the syntax will be for, and in brackets you will write your variable k. This variable k will start from 0 and will run till 5. Okay, and I will display my k, and automatically for a for loop will increment k after every loop. Okay, so I do not need to specifically write that down, and then I'll end my for. So let's see what my output is. As you can see, it prints out k is equals to 0 till k is equals to 5. Now let's go to a while loop. Okay, so in a while loop, basically you need to specify what your initial value of k is, and then you will write the condition after you write while. So while k is less than equals to 5, it will print k. And unlike a for loop, you have to specifically write your incrementing k by 1. Okay, so let me show you. I is equals to 0. Okay, that's my initial value of I. And then while I'll write my condition, while k less than equals to 5. Okay, I will display my I, right? And I will increment my I by 1. So I can do this in two ways. I can either write I equals to I plus 1, or there is a shortcut to it. I can write I plus plus. So I plus plus, and I do not want this to be displayed. I want only the value of I to be displayed to the user. So I'll press a semicolon. Okay, and then I'll end it. To save. And then, okay, yeah, my variable is I, not k. So I'll save it and then run. As you can see, it's the same output as before. I is equals to 0 till 5. And yeah, this is another way of getting this output. So I will again take a 1-minute break. In case you guys have any doubts, you can ask. Somebody raised, Archana raised her hand. Do you have a doubt? Show the code again, please. For loop. Okay. This is the code for both the loops. I hope that's clear. Can you show the previous file of printing an array? Yeah, sure. So it's just simple. To print an array, you'll just type the array's name. Like you will first define what your array is and its elements, and you will just type in the array name. That's all. You can do the same for a 2D array as well. Okay, then if the increment operator is showing errors, then you can just use I is equals to I plus 1. That's just a shortcut. With the end statement, no, the end statement wouldn't have an indent. It should be from the start of the line. Yeah, it should work. Okay, what will it display? 2:6:9. So it will display 2 and 8, right? Because 2 plus 6 is 8, and 8 plus 6 is 14, which is more than 9. So it will display only 2 and 8. You can try that out. How to print only one? Yeah, using indexing. Like I'll just show you in the presentation. So I've defined my array. S is equals to 2, 3 in the first row and 4, 6 in the second row. And if I want to get 3, the element 3, I would use indexing. The index is 1, 2, right? So I'll just simply give a variable to that to the element, like second is equals to S, and in brackets I'll write the index. So 1, 2. And that's it. I'll just print the output. Okay. And I'll continue now. So loops is done. Now functions. So a function is basically a block of code. And suppose you have a set of operations in your main program, the main program that you will run. And in that program, you have many operations that come again and again, that you have to write that operations again and again. Like suppose you are adding two numbers. So you have to again, and you're adding those two numbers again and again in your program. So you can, instead of doing that, you can create a function which adds two numbers. And in your main program, you can call that function again and again. So you'll give some inputs, like you're adding two numbers. Suppose the function is adding two numbers. So we'll give you, so from the main program, the program which you will run, you'll given the values of the inputs to the function. Okay, and then the function will do whatever it's expected to do, and will return a value back to the main program. And whatever it returns will be used to continue in the rest of the program. Okay, so each function usually has its own .m file. In a sense, you create a new file for a function, and it's preferred that way. It's recommended. Okay, so let's see how do we create a function on Octave. So we'll just we'll do this one. We'll do this example only. We'll create a function to add two numbers. So we'll create a new file first. And this is how you define a function. Function, you write in function, and what you want to return. So that is denoted by ret. Okay. So ret is equals to my function name. So I'll call my function as sum up. Okay, because it sums up two numbers. So sum up, and then my two numbers, a comma b. The values of a comma b will be taken from my main program. Okay, so function ret is equals to sum up a comma b, and then I'll define what my ret is. Like I'll define what my function is. So ret is equals to a plus d. Okay, and then I'll end my function. So end function, and there should not be any space between end and function. Okay, so let's check our function once. All right, we'll save this and we'll call it sum up. And in our main file, basic.m, we will create a program which will take in two numbers from the input, give it to the function, and get the output from the function. Okay, so let a be my first number. So a is equals to input. Enter your first number equals to input. Enter your second number. And then let's see, store the sum of a and b. And then, no, I mean, we are using a function, right? So to call the function, you will write your function name, sum up. Sum up is my function name. And in the brackets, you'll give the variables, like what inputs you are giving to the function. You're giving a comma b, right, to the function. So we'll write an a comma b. Okay, so let's save this and we'll run basic.m. So enter my first number 12, enter 13. Oh, I haven't wait, let's refresh Octave, because sometimes it throws an error when you create a new function. We'll restart Octave. And let's open my folder first. And let's run basic. So 13. Yeah, as you can see, 13 plus 12 is 25. So in case after you create a function and it throws up an error, you restart your Octave and then it's going to work. I don't know why this error comes up, but something in Octave only. I don't know. So yeah, I hope you guys have understood functions. Let's proceed. So I've written the same code here. You can refer to it when we send you the presentation. Okay, now conditional statements. So if, else if, and else. So suppose a certain condition is met, you want a certain operation to happen, right? Like it can be to display a message to the user or something like that. So if a certain condition is met, you want something to happen. Or if some other condition is met, you want something else to happen. And if no condition is met, you'll either leave the program like that, or you want like something else, like some other thing to happen, right? So for example, a simple example is divisibility test of 2. Basically, if a number is even, the program will check if it leaves a remainder of 0 on division by 2, and it will print that your number is even. And if the number is odd, like that you will use an else statement for that. So for all other cases, it will print your number is odd, right? So let's see an example on Octave. Let's go to our main file and okay, and let's create a program for eligibility to vote. Okay, so so it depends on the person's age, right? So let my user give his age. So age is equals to input. Enter your age. Yeah. And state my if statement. So if age is greater than 18, it will display you can vote. Okay. Now there's one more thing called else if, and it's basically if some other condition is met, it will display something else, right? So else if age is equals to 18. You write 2 is equals to it because this checking if it's true. Okay, so that's why you use 2 is equals to is. So this it's your first time voting. Okay. And else for all other cases. And the all other cases here is basically if you're under the age of 18. So else is you should grow older. Okay. And we'll end this. Uh, Save this file. We'll just check our code once. Let's run this. So enter my age. Suppose I'm 19 years old. It says you can vote. And I'll run it again. And if I'm 18, it should give output. It's your first time voting. And if I am 2 years of age, it should say you should grow older. Yeah, fine. So yes, whatever I've done is also written here. You guys can refer to it after the session. And with this, we have completed the basics of Octave. And the attendance forms have been circulated, I guess, or will be circulated on Teams. So you guys can quickly fill in your attendance. And now I'll be taking your doubts. Which code should I show? Please go slow. Okay, fine. I'll keep that in mind. I'll show functions again. So this is how you can create a function. So for creating a function, this is the syntax. Function ret is return. Return what should return? It should return the whatever the function is returning, right? So ret is equals to the function name and the two inputs it's being given. So a comma b, and then what the function is doing. It's adding two numbers, right? So ret is equals to a plus b, and then we'll end my function. So I hope it's simple. Running a file is hard. I'm always getting only basics in my output. Are you saving your file? So completed soon. Yeah. I think the chat modes have answered most of your doubts. You guys can quickly fill up your attendance. I'll wait for a few minutes. No, the meet is not over. The main part is still left. Can you show the if else if code? Yeah, sure. The outputs. Where to see the output of the code? You see the output of your code in command window. Like on the bottom, you see 4 tabs, right? So one of the tabs is command window. So you click on that, and this is where the output of the code is. How to save the file as an Octave file? It keeps getting saved as a document file. Where are you writing your code? Are you writing it in the text editor of the Octave? Yeah, it should be saved as an .m extension. Let me show. Yeah, don't. So are you saving the file with a .m extension? Once check that. I'll show the function syntax. This is just a very basic function. Uh, I'm just covering up basics for now so that we can cover up as much stuff as possible. Not enough input arguments. Error in voting. That is equals to a plus b. No, you have to run you're running your function as well. Don't run the function. Just like run your main file. So you have to right click on your file name of the main program and then press run. Once Vasudev, once try refreshing Octave again. Such errors come. If you have written your code properly and you're confident about it, close Octave and run it again, and then run your file. Okay, so let's continue. So we have completed the basics of Octave, and now we can start getting a code for the Euler's method, right? So let's have a recap question first. If you guys have paid just a little bit of attention also in the previous part, you guys should be able to answer this question. The chat mods will be putting up a poll for this. So the question is, to solve the Euler's method, what should be given to us? Option A, initial conditions. Option B, the step size, h. Option C, the derivative function. Or option D, all of the above. I think you guys would have answered by now. Yeah, all of you have given the correct answer. Yeah, fine. Guys, good job. So let's continue. The answer is obviously D, as you guys would have already answered. We need the initial conditions x1, y1, the step size h, and the derivative function dy by dx. Okay, so getting started with writing a code for Euler's method, let's see for an example. Let our initial conditions be for the point 1, 1, that is x1 is 1, y1 is 1, and the derivative function is 2x, and our step size h is 0.01. Okay, so if you would have guessed, the function f of x will basically be x square, right? You can easily understand that. So now we'll basically first write a code to find the next point, x2, y2. So for that, we will first initialize what our initial conditions are, our step size, and our derivative function. And then we will be writing the equations for x2 and y2. x2 is basically x1 plus h, right? The next point after x1 separated by a distance of h. And y2 will be y1 plus h times f1, the formula for Euler's method. And then we'll print what x2 and y2 is. So as you can see, the output is like x2 is 1.01, that is easily calculated. And y2 is 1.02, that's the output for y2. And as you can see, this is a very good approximation because actually y2 should be x2 square, right? 1.01 square, which is 1.0201. And this is a very good approximation. Like 1.02 is a very good approximation. Okay, so now to write a code for the Euler's method to find the remaining points of x till the point we require. So we will have to repeat the middle steps, right? The two steps. x2 is equals to x1 plus h, and y2 is equals to y1 plus h into f1 till a certain condition is met. So we'll be repeating these two commands using a loop. Okay, so I haven't coded for the last one because it's pretty obvious. I'll code for this. So this is the code for it. I'll code it on Octave. Okay. So let's initialize our step size, so 0.01, and let's create an array for x, which will have like the array will have the elements, like the positions of x will be stored in the array, right? So we'll get an array for x. X is equals to an array for it. So x is equals to 1 colon the step size h colon 3. The output of the program should basically be like the code should basically run till x is equals to 3. So basically I want my y for x equals to 3, right? So that's the aim for this program. So x is equals to 1 colon h colon 3. That's my array. Okay, and our initial condition for y. So and I'll be creating an array for y as well. So the first element of y array will be 1. It's my initial condition. My initial condition is 1, 1, right? So 1. Okay, and now we'll be creating a for loop, right? So my for loop will run from, let's give an index k. So this k will iterate after every loop. So for k is equals to 2, I'll explain why is it from 2 to length x later on. Okay, I'll explain why this is the case. And see, I haven't defined what my function is. My function for derivative is f of x is 2x, right? F dash x is 2x, right? So because that varies with every point, right? So I'll write it inside my for loop. So for f, I'm like my derivative, I'm calling it f, and I'm defining it using an array. So for f, and for the k minus 1th element of f is basically 2 times x, the k minus 1th element of x, right? So semicolon, and then we'll write the Euler's method equation, which is basically y of k is equals to y of k minus 1, the previous element of the array, plus h times, okay, f of k minus 1. Now let me explain what I've done if you guys are confused. So I'm running my for loop from 2 to the length of x. Basically, I'm running my for loop from 2 till the number of elements that x contains. Okay. And why am I doing that? Because we already know what the first element is, right, of x and y. So I'll be running it from the second element till the length of x. And then I'm defining my function at every point of x. So f of k minus 1 is equals to 2 times x of k minus 1 because f dash x is 2x, right? So, and that changes at every point. And then I'll be using this function to create an equation for y, like which depends on x. So y of k, the kth element of y will be y k minus 1 plus h times f k minus 1. Okay. And now I'll be plotting this. This is how you plot something. Plot x comma y. Okay, and let's check our code. It should run fine. Yeah, as you can see, it generated a plot. I close that one sec. As you can see, this is what the plot comes out to be. Now it's not very clear that if it actually like represent y is equals to x square, right? So let me print the array elements of x for some random indexes, x and y for some random indexes. So let me just see for the 21st element of x, like what the value is, and the 21st element of y. Okay, and for like, and let's also do the same for the 41st element of x and y. So let's see what the output is. Yeah, so as you can see for x21, it says 1.2 and y21 it says 1.38, which is a very good approximation to 1.2 square, 1.44. And if you want an even better approximation, you can reduce your step size like to like 0.005 or something like that. Here we have used 0.01, right? So you could reduce your step size. And x41 is 1.4 and y41 is 1.956, which is a good approximation to 1.96. Yeah, and that's it. That's how you code for the Euler's method. You can refer to this. And this is a code template for the Euler's method. Here you can just replace your values of h, your initial value of x and your final value of x. So x is equal to dash colon h colon dash and the initial element of y. And then you can create a for loop for this is obviously standard. K is equals to 2 till length x. And you can define what your derivative function is. F k minus 1 is equals to what. And then you can get your array elements for y. And then you can plot it. Okay. So is there any doubt till now? What does k mean? K is just an index. I'm using k to so that my for loop runs. Right? I need to define an index k so that my for loop will run. So why we took k is equal to 2? Yeah, one second. So we took k is equals to 2 because we already know the first elements of my x and y array, right? That's the initial condition. We already know my initial condition. So we already know what the first elements of x and y arrays are. So that's why I'm starting from 2. And you can say that k is the index of the element of x and y. So that's why I'm starting my for loop for k is equal to 2, and it will run on till the length of x, basically the number of elements in x. Why should we give k minus 1 instead of given k is equal to 1? Why should we give k minus 1 instead of k is equal to 1? Where? Yeah, show the code. Okay, I'll explain the code once again. So see, first we need to define what our initial conditions are. I've been given with my step size h. So I'll write that h is equal to 0.01. And I'll be defining my array x, which will have all the positions of x. So my elements of the array x will be 1, 1 plus h, 1 plus 2h, and so on till 3. So I am creating an array for x. So this is how you create an array. X is equals to, I haven't written boxes, but that's fine. Like either you can create box or Octave will understand if you do not write boxes that you're defining an array. So x is equals to 1 colon h colon 3. And to store the values of x, basically, uh, like I want to store the values of y corresponding to x, right? X has many elements in its array. So I want to store basically y equals to x square. Basically, I'm doing an approximation for y equals to x square. So I'll be storing the values of y for each x in its array, in y array. And the first element of y is 1 because that's my initial condition. 1 comma 1 is my initial condition. Okay, so we have been given with our initial conditions. We have specified them. We have initialized them. Okay, and now we'll be creating a for loop to find the remaining values of y. We already know the values of x, right? 1, 1 plus h, 1 plus 2h, and so on to 3. Now we need to find the corresponding values of y. Okay, so we'll be running a for loop for that. And my for loop will run from 2, the index 2, till the number of elements that are contained in my array x. And for that, I'm using an index k. I'm defining a local variable so that if I can, I'm defining so that I can get the remaining elements of my array y. And since at each x, my derivative is changing, I'll be defining my function, the derivative function inside the for loop. So it's basically f of k minus 1 is equal to 2 times x of k minus 1, right? Because for getting the kth element of y, x values at k minus 1. So we'll be, and then after we write the derivative function, we'll be writing the equation for the Euler's method, which is yk is equals to yk minus 1 plus f k minus 1 into h. Okay, and then I'll be ending this loop. And I'll be plotting x comma y. And I guess now you guys must have understood it. Did you guys understand this? Yeah. Do you guys need more time to write the code or something? Why we took x to 3? Okay, you can take x to whatever you want. I just took it to 3 to plot the data. Like I want my final value of x till 3. You can, yeah, it's random. Okay, then I'll guess I'll continue. So yeah, this is the code template for the Euler's method. And now let's see an application with which we can solve the Euler's method, which is the law of radioactive decay. dn by dt is equals to minus kn. You guys must have read this somewhere in your 11th and 12th grade. So it's obviously the same code, except here I've just replaced the variables x and y with t and capital N, just for better understanding. And here I have taken the input for decay constant from the user, and using that, it will plot the data. So after I take the decay constant from my user, suppose the user gives a decay constant k is equals to 2, it will plot the graph. And this graph is very close to the actual graph. Okay, you guys can refer to this example. I'm not coding for it because it's very similar. Okay. So now let's go to the next method. So whatever Euler's method was for, it was for ODEs, right? Ordinary differential equations. This finite differences method, a new method, is for solving the partial differential equations, okay, PDEs. So you know what partial derivatives is, right? Like suppose a function f varies with x and t. So dou f by dou x will indicate the partial derivative of f with respect to x. And you basically have to differentiate normally, but you have to keep all other variables constant. So that's what a partial derivative is. So how do you go about this method? What is involved in this method? So you replace the derivatives with algebraic approximations. So you know what f dash x is, right? F dash x is nothing but as limit h tends to 0, f of x plus h minus f of x by h, right? So you'll be replacing that derivative with algebraic approximations. You'll be replacing that derivative to get an algebraic equation. And if you have many what's it called derivatives. You can replace all of them, and you'll get. And after solving the algebraic equations, you'll get an approximate solution. All right. So let's see that using a simple example. This is not a PDE, I know this is an ODE, but we'll start with ODEs and then go to PDEs. Okay. So let f dash x be f of x and f of 0 be 1. And it's obvious that the solution is e to the power x, right? Now we'll use our finite differences method. So we know that we have to replace f dash x with f of x plus h minus f of x by h. And we'll assume that h tends to 0. We'll not specify that. We're already assuming it. And now we'll replace this f dash x with the algebraic expression, and we'll get a new expression after simplifying the terms. We'll get f of x plus h is equals to 1 plus h times f of x. And our initial condition is already given to us. F of 0 is 1. And in this equation above, if we replace x with 0, you get f of h, which is 1 plus h. And then after you keep on replacing terms like that, you'll get f of 2h is equals to 1 plus h whole square, and so on. And basically, if you haven't already understood, you'll get f of kh is equals to 1 plus h whole to the power k, right? So, but notice one thing, f of x is our actual solution, but all this f of 0, f of h, and f of 2h just approximate the actual solution, right? So there's a conflict of notation. I cannot write simply that f of kh is 1 plus h to the power k. I cannot write f of x is equals to 1 plus h to the power k, right? Simply because it's just an approximation. So for that, we'll define a sequence fk. Okay, this sequence fk is basically an approximation for f of x. Okay, where x is kh. I hope you guys can understand that. And what is my sequence? How to get the next term of the sequence? Fk plus 1 is equals to 1 plus h times fk. Okay, and our initial condition is f of 0 is 1, right? It basically means f0 is 1. Okay, so I know I'm considering here my h is 0.5, which is obviously quite large. So we'll get a bad approximation. But just for simplicity, just for better calculation, I've taken a big value like h is equals to 0.5. You can always take 0.01 to get a better approximation. So my first term of my sequence, f0 will be 1. And at what point is this? It will be at x equals to kh. Right. So here k is 0. So 0.5 times 0, which is 0. And my next term of the sequence, f1, will be 1 plus h. So 1 plus 0.5, 1.5. And this will be at x equals to 1 times h. So 0.5. And you can write the remaining terms of the sequence, f2 and f3. f2 is 1 plus h whole square, f3 is 1 plus h whole cube, and x equals to kh for k is equal to 2 and 3. Okay. And if we just compare these values to our actual answers of e to the power x for x is equals to 0, 0.5, 1, 1.5, I mean, you can write the answers and let's plot the data. Okay, let's see how well our approximation is. So as you can see, they're quite close. They're not that close because we have taken a bad value of h, but it's quite close. So we can use the method, this method to solve PDEs as well. Let's take an example to do that. But before that, do you guys have any doubts? Let me continue. Okay, so we'll be seeing the heat equation. We'll use the method of differences to solve the heat equation. This is a PDE. So what is the heat equation? The heat equation is UT is equals to KUXX. But what is U? What is T? What is K and X? So consider that to be a rod lying on the x-axis, and one end of the rod is at x equals to 0, and the other end is at x equals to L. Okay, and assume that this rod is insulated, so there's no heat loss, and like we have been given an initial conditions for the temperatures which vary with x. So at t is equal to 0, we have a function of t with respect to x at the initial time that t is equal to 0. Our aim is to find the temperature as a function of x at some other time t. So that is our aim. So you can do that using this heat equation. Ut is equals to kuxx. Ut is basically dou u by dou t, the partial derivative of u with respect to t, and kuxx is dou square u by dou x square. Okay. So we can use the approximation what we have learned before for the e to the power x thing. Dou u by dou t approximates to ux comma t plus delta t minus ux comma t by delta t, where delta t tends to 0. I'm not writing that because it's assumed. And in case you guys don't understand what this equation is basically for a constant x, we're differentiating u with respect to t. So for ux comma t plus delta t minus ux comma t by delta t approximates dou u by dou t, right? So this is called a forward difference approximation because I'm taking a point after t plus delta t, right? So it's called the forward difference approximation. Similarly, you can write dou u by dou x, which is ux plus delta x comma t minus ux comma t by delta x. And here t is constant. Okay, so observe that in our equation, it's ut is equals to kuxx. So uxx, right? So we are differentiating it twice. So basically, uxx is nothing but dou ux by dou x, right? So in this equation for dou u by dou x, we'll replace u with ux. So dou ux by dou x is will approximate to ux x plus delta x comma t minus ux x comma t by delta x. Okay, and now we again need to use our approximation for ux. On the RHS, you can see ux, right? So we will use our approximation to replace ux. So what do you think will be good? Like again, using a forward difference approximation for ux, or we'll use a backward difference approximation. By backward, I mean we'll replace plus delta x with minus delta x. So I'll not be solving, I'll not be like showing you what doing a forward difference approximation again does. We'll just assume that the backward difference approximation gives you a smaller answer. You guys can check it out. Okay. So a backward difference approximation is basically replacing delta x with minus delta x. And so just telling you what backward difference approximation is, dou u by dou x will approximate to ux comma t minus ux minus delta x comma t by delta t. And we'll replace this in the above equation, in the above approximation. And we need this dou u by dou x at two separate points. At x equals to x, firstly, as you can see in the equation, and at x equals to x plus delta x. Okay. So what will dou u by dou x be at x plus 2x and x plus delta x using the backward difference approximation? It will be this ux x comma t at x equals to x will be ux comma t minus ux minus delta x comma t by delta x, and ux x plus delta x comma t will approximate to ux plus delta x comma t minus ux comma t by delta x. Okay, so hence if we plug this in to our uxx equation, we'll get dou square u by dou x square. Okay. So these are just the steps, dou ux by dou x. You put in the approximation, the forward difference approximation. Then for each of the terms, you put a backward difference approximation. And when you simplify it, you'll get this expression. It's not that simplified, but it's much smaller than the equation you would have gotten if you used forward difference approximation twice. Okay. Now observe that I've first done a forward difference approximation and then a backward difference approximation. So intuitively, you can tell it's a central difference approximation, right? Okay, so let's combine these two equations in our heat equation, and then we will get our our heat equation is ut equals to kuxx, right? So we'll replace these two equations and that to get this. And basically, what are we solving for? So just observe this equation carefully. You can see this equation has functions like u is always a function of x and t, right? So it's the u is getting evaluated in all terms at the time t. But in only one term is getting evaluated at t plus delta t. And that's what we require, right? We are solving the temperature at the next time point after some time interval where we want to find the temperature with respect to x. So we are basically solving for ux comma t plus delta t, right? So ux plus x comma t plus delta t will approximate to ux comma t plus alpha times ux plus delta x comma t minus 2ux comma t plus ux minus delta x comma t. Now what is alpha? Alpha is nothing but k delta t by delta x square. Now let's just intuitively think, what is this telling us? Like how do we what does this represent? So basically tells us if we have the temperatures at 3 consecutive positions at some time t. If we have the temperatures at 3 consecutive positions at some time t, like at x plus delta x, at x and x minus delta x, if we have the temperatures at those 3 points, you can find the temperature of the middle point, which is x. At some other time means the next time, which is after that interval of delta t, at t plus delta t, right? So that is the intuitive feel of that. So do you guys understand this? Yes. Okay, cool. Then let's continue. Okay, now whatever okay, fine. I've written whatever I had told just like a minute ago, that if we have the solution at 3 positions, x plus delta x and x plus 2 delta x at time t, we can find the solution at the middle position at time t plus delta t. Okay. So this is the equation again. And I had assume that the rod lies between 0 and capital L. But for the sake of having a proper proof, we will write, we will have x from A to B. Basically, the rod lies between A and B for time t is greater than or equals to 0. Okay. And what do we seek? We seek approximate values for u x comma t at some position x and some position and some time t, right? So we will first divide the interval a comma b. We'll first divide the x-axis where the rod is lying into n subintervals of with delta x equals to b minus a by n. And the endpoints of the subintervals will be obviously be given by xi is equals to a plus I delta x, right? So x0 will be a because I is 0, and x1 will be a plus delta x, x2 will be a plus 2 delta x, x3 will be a plus 3 delta x, and so on. And xn will be a plus n delta x, and n delta x is nothing but b minus a. So xn will be b. Okay, so hope you guys understood that as well. And similarly for delta t, we can write tj is equals to j delta t, where j is equals to 0, 1, 2, and so on. Okay, so I is basically the index of position and j is basically the index for time. Okay, so let's replace these because similar, like remember in e to the power x also we had done such a thing. So we'll do the same thing again here and we'll get a new equation. Okay, we wanted an approximate solution to u x comma t or u I comma j, where I is the index for position and j is the index for time. Okay, so if we replace all that, we will get this approximation. U I comma j plus 1 will approximate to u I comma j plus alpha times u I plus 1 comma j minus 2 u I comma j plus u I minus 1 comma j. And if you guys don't understand like what are we doing in this, we can understand this by a stencil. Okay, so in this stencil, I is the x-axis and j is the y-axis. And as I've told you before, if in a row we know the values of three consecutive positions, then you can find the value of the middle position at the succeeding row in the above row, right? So you can find ui comma j plus 1. Okay, and then if we have our initial conditions, if we have the bottom row the u values of the bottommost row, then one row, you can find j is to 2 row, and then you can generate all the other rows, right? So observe that you will get a triangle and not all the data points. You will get only a triangle because you're getting only the middle value, right? You're not getting the other values. So what about like how do we find the data points for all other values, like on the sides and on the top, because the triangle will end, right? So how do you do that? So for that you need to declare your boundary conditions. So what is my boundary condition? I'll assume that my boundary conditions is that the temperature is always 0 at the endpoints. For any time t, I'm assuming that my temperature is always 0 at the endpoints. So if you write that using indexes, you'll get u 0 comma j is equal to 0 for all j, and u capital N comma j is equal to 0 for all j, basically. Yeah. So you get all the data points in your stencil, and yeah, that's it. That's basically it. Now you need to just code for it. So first there'll be a lot of values to initialize. Okay, and after you initialize all these values, you have to write your equations for x and your initial value, and then you have to write your code for the partial for the PDE. So let's open Octave and do that. But before that, are you guys clear with the method of, I mean, guys clear with heat equation? Did you guys understand the heat equation and what we are doing? Okay. So yeah, we'll be sharing the slides to you. You can go again. I know it's a little hard telling orally, so you guys can see that. Okay, let's open Octave and code for it. So okay, so first we need to define the length of the rod. Capital L is equals to 1. Let's have capital L to be 1. Okay, and let my I'm running my code till t is equal to 0.1 seconds. Okay, so let's declare my variable t, which is 0.1. Okay, and then I will declare my heat constant as well. So let my heat constant be 1, taking very simple values. So L, T, K, and what else? Yeah, we had divided our x-axis into subintervals, right? So let n be 10. We're dividing into 10 subintervals, and let m be 50. We are having 50 time steps. Okay, so if you guys don't understand, we'll be calculating the temperatures for 50 values of time, right? For 50, after 50 intervals of time, we'll be noting down our temperature. Okay, and then we know what our dx is. Our dx is basically capital L by m by n. Okay, and then our dt will be capital T by m. Dx is basically the, the length of each subinterval, and dt is basically the length of the time interval. So yeah, L is equals to 1, T is equals to 0.1, K is equals to 1, N is equals to 10, M is 50, dx is L by N, and dt is T by M. So we have given our initial conditions and everything. Now we'll create an array, like how we had created an array for position like x in Euler's method. We'll do the same thing here. We'll create an array for x. Okay, so for I, let every index of my array be denoted by I. So I, this for loop will run from 1 till n plus 1. I'll explain why 1 to n plus 1. And then each element of my array x will be xi is equals to I minus 1 times dx. I'll explain why this is true. And then I'll end. Okay, I'll end my for loop. So what is this? Like, what are we doing? So for the first element of x, the position is obviously 0, right? And for my second element of x2 will be dx, and my third element x3 will be 2dx. So my first element will be 0, second element will be dx, third will be 2dx, fourth will be 3dx, and so on. And we are running our total n plus 1 because x n plus 1 will be n times dx, right? So we need to define what the last element of our array is. So that is nothing but n dx, and n dx is basically L. So our rod is lying between 0 and L, and hence we're doing this. Okay, and now we have gotten a position array. Now we'll define our initial conditions. So for I is equals to, again, 1 is to n plus 1, the same logic as before. We will have our initial condition array. I forgot to add a semicolon here. Semicolon is important. So let's have our initial condition. The array name is u naught. Okay, so u naught I, every element of the array u naught will be, like, suppose our initial condition is sin pi x. Okay, so sin pi is already defined by Octave. You do not have to define what pi is. So sin pi times x. Okay, and it will be sin pi x, where x is the array elements, right? The array elements of x. So sin pi x of I, right? And then semicolon, and we'll end this for loop as well. Now we'll be coding our PDE. So we want the values of temperature for 50 intervals of time, right? After 50 intervals of time, we want what the values of temperature are with respect to position x. So for j is equals to 1 till m. M is basically 50. So for j is equals to 1 till m, we're getting a for loop for that. This for loop will basically increase time, basically go to the next row. But what about increasing the position? We need to increase the position as well, right? For finding the values of temperature with respect to x. So for j is equals to 1 to m, we'll write another for loop for I is equals to 2 to n. Okay, now why am I doing 2 to n here and not 1 to n plus 1 as before? I'll explain that. It'll be clear when I write the code. And now I'll be writing the equation, the PDE, the approximated form of PDE which we had derived. So I've got it written here. I don't remember what I got it written, so I'll write it. So yeah, so my next row, let's give an array for that. It will be u1. Okay, I, the element I of u1, the equation for that, u1 I is equals to u naught I. I'm basically writing the equation what we had derived, u1 I plus alpha times u naught I plus 1 minus 2 u naught I and plus u naught I minus 1. Yeah. And then remember to close all the brackets or else it will throw up an error. So yeah. And now we'll end we'll end only one for loop. So we have gotten our the function of temperature with respect to x at the next time, right? So we'll end this for loop, and then what we have, see, we have u naught, we have gotten u1. Now how to get u2, u3, and u4 and so on? You cannot keep on defining u2, u3, u4 and so on, right? There's a shortcut for that. So you have already been given u naught. You have found u1. What you can do is you can make your u1 u naught. So when your u1 becomes u naught, basically j is equals to 1 row becomes u naught. You can, this for loop will run on for 50 time steps, right? So in the next for loop, it will find out what u2 is. So, and then when you make this u2 your u naught, your initial value, it will find the next values, the next row values. Okay. So I hope you guys can understand that. But first, we should remember about the boundary condition. We have to write that as well. So u1 at the boundaries will be 0, right? And what? Yeah, and let's make our u1 u0. Let's make our u1 row u0 so that the for loop continues. So u0 is equal to u1. What is u0 equals to u1? Basically, whatever elements are in u1 will be now stored in u0. Okay, and that will be used in next for loop to create the next row. Okay, and then that's it. We'll end this. So now let me explain about why have I taken the indexes, like why have I taken j is equals to 1 to m and n is equals to 2 to n. So remember when I told you that if we haven't specified the boundary conditions, we'll be getting our rows, like the data points, in a triangle format. So for that, like, look at that equation. U1 I is equals to U naught I plus alpha times whatever. So you won't be able to get U1 1 because that's the first element, right? You'll be able to get U1 2 because that will come out from, like, that can be considered middle point, right? So if we consider at the previous times, we can consider temperatures at the previous time step for 3 consecutive values. Okay, so that's why we can get all the values for the next row from 2 to n, but not the boundaries. So hence I have created my for loop to go only from 2 to n. Okay, and yeah, that's it. I guess we can plot x. We can plot u1 with respect to x. Okay, and should be written x comma u1. Whatever is in the x-axis should come first, and then to make, or actually let's just run this code and see if it runs properly or not. So run. Okay, there's an error in the syntax. Yeah. So guys, always be careful. Your code will not understand what 2x is. It will understand what 2 times x is. So you have to put an asterisk. And then let's run it again. Oh, I haven't defined what my alpha is. So let's define what alpha is also. Alpha is basically k into dt by dx square, right? So let's check out the plot, what it has generated. So this is the plot. And if you guys can trust that this is the actual answer, what the plot will be for variation of t with respect to x at 0.1, if you can trust it, you can. But if you want, if you want to prove that it is so, you can use a pen and paper and you can calculate all the values. But that will take a lot of time. So this is why you can just compute it numerically like this. Okay. And now observe this plot. It is not expressive. We do not know what x and y is. We haven't given a title, right? So to show that, we can give x label and y label. This is how you do so. X label x and y label y, right? Y label u1 or y label temperature at time 0.1 seconds. And let's give it a title as well. Title t versus x at t is equal to 0.1 seconds. Okay, so and now let's run it. Control save and run. So as you can see now you have got labels for the x-axis and y-axis, and you've got a heading as well. You can change the sizes of that, but we won't be discussing that now. So you guys have any doubts till here? Why do we use sign here? We're just giving an initial condition. You could have had any initial condition, right? 2x, 3x, 4x, or some function. So I use this trigonometric function sin pi x. So what is k here? K is the heat constant that is defined, that is physically defined by the properties of the rod. We won't discuss that. Index exceeds the number of array elements. Index must not exceed 1. Okay, then check your code once. I'm not sure which index I'm talking about. Which index I'm talking about exactly? Can you show alpha once again? Alpha is k times dt by dx square. Alpha is k times dt by dx square. Alpha is equal to k. Index exceeds the number of array elements. Did you define what your Pruthik, did you define what your position and initial conditions are? Because your code looks fine to me. Yeah, I'm not sure why it's throwing an error. And check your code again. Anyway, I'll be sending the code in the presentation. So just check how you have defined your position array and the initial conditions. So yeah, that's it from my side. So yeah, thank you guys. There's one very interesting problem on the method differences in the problem set that you will get. It's slightly involved, slightly more involved. But if you guys have understood the method of differences properly, and if you guys just refer to the slides once again, I'm sure you'll be able to answer it. It's a very interesting question. So thank you guys. If you have any doubts, you can ask. I'll answer them. You want to see the code? Okay, I'll share it. Also, the code will be present on this thing in the presentation, so you can check it. There are multiple pages of code. Yeah, but the feedback form has been shared. Please click on that and fill in your feedback. And so guys, we have our YouTube channels and our LinkedIn page. It will be very good if you guys could follow that, and we'll be regularly updating that those two social media accounts with interesting problems for you to solve, and events such as this, so that you guys can participate. And we have our website as well. The links of the website, social media, LinkedIn will be shared in WhatsApp, so you guys can keep track of those as well. Thank you.
Thank you all very much for attending. We'll be continuing in the next session on 21st June on Friday. We'll be sharing the problem sheet in some time. Please submit the problem set 1 by the end of today if you have seen the extension of the deadline to tonight. Uh, all the very best and hope to see you will be very eagerly waiting for you in the third session. Thank you.